We are now covering part 3 of our lesson on factors and zeros of polynomials. We're going to be using some factors and zeros ideas to look at building up functions and understanding them further in this lesson. Our goal will be to write an expression for a function that has specific horizontal intercepts. For starters, we are looking at two different functions at the top of this slide. M of x, which is x plus 3 times 2x minus 5, and k of x, which equals 3 times the x plus 3 times 2x minus 5. How are the two functions alike? How are they different? So if we just look at the functions themselves, they are alike because they have the same factors, in parentheses at least. We have x plus 3 and x plus 3 that are the same. And we also have 2x minus 5 and 2x minus 5 are the same as well. So if we set each of those matching factors equal to 0 and solve for x, you would have for the blue one that one x-intercept would be 5 halves, or 2.5, and the other one would be x equals negative 3. So they share two x-intercepts. The difference is the 3 that we see at the front of k of x. And that, if you remember from our prior part of this general overall lesson, that is going to be dilating the polynomial function that k of x is going to be producing. So now with the graphing window question, part 2, we're looking at from x is from negative 5 to 5, and y is from negative 20 to 20. So let's look at our Desmos graph to analyze that a little bit. In comparing these two, are negative 5 to 5 and negative 20 to 20. We can see that viewing window right there. We can see most of our red one, but we can't really see all of our blue one. Looking back at our slides, when it says show all intercepts, so it says shows all intercepts of the graph of m of x. What that means is that we can look at function m, and I can see that function m has an intercept of negative 3 and 2.5, like we already discussed, but it also has a y-intercept of negative 15. If you recall from a prior part, if you take the n numbers and multiply them, 3 by negative 5, that is why we have negative 15 as a y-intercept. But we cannot see all of the intercepts for our blue function. We know already that it shares x-intercepts. So if I would have to zoom out until I can see my y-intercept of negative 45. And if you look back at our function, 3 times 3 times negative 5, that is equal to negative 45 for our function in blue. So that covers all their similarities and differences. Same x-intercepts. It's opening up in the same direction, but k, our blue function, is dilated by 3. Moving to slide number 2, a little bit more of a discussion on choosing viewing windows, which is always easier in Desmos. So we have this girl, Mai, in her class. She's saying that the parabola p of x, which you see to the left, looks like a parabola, and so that means it must be quadratic. So if we would look at this function, that's just based on the viewing window they have there, it seems to be correct. So let's look at Desmos to see if she really is. And so we start out with negative 10 to 10 for the x-axis and positive 40 down to negative 40 for the y-axis. And so that's what we're looking at right here. And we can see it's the same picture we saw earlier, and it seems like we had our x-intercepts and we have our y-intercept down here, and it does definitely look like a parabola. So looking at the questions they asked, well, is it correct? Well, if we zoom out a little bit, well, now that we've zoomed out, so we can see a little bit more for x and y. You can see that on Desmos, here is our domain is negative 40 to 40, and our range is negative 160 to 160. And so we have that as our domain and range, well, now we can see it's no longer, it's definitely not a quadratic parabola. It is now more of a cubic polynomial shape, and you can see that more of it is kind of seen the farther you get out and the farther you zoom out, which is easier to see in Desmos, a little bit harder to do on a graphing calculator. So we've zoomed out and we saw more features of the graph. So if we wanted to think about how we would see all of the graph, a great rule of thumb would be to see, well, can I see the y-intercept and also see all of my x-intercepts? So using number 3 as an example, if you look at each one of these 4 parentheses, they would show us, based on our prior knowledge, that our x-intercepts are -1, 1, 2, and 28. Now, if I want to know my y-intercept, I would grab a different color and do 1 times -1 times -2 times -28. And that would mean, well, we have -1. -1 times -2 is 2. 2 times -28 would be -56 for our y-intercept number. And that we can take back to our graph and look at what that would end up looking like. So we can take that graph of x plus 1, x minus 1, and then x minus 2, x minus 28. Now we can see sort of everything, but remember, we want to include all of our x-intercept and our y-intercept. So in order to see everything, we would want to include all of those. So maybe we would have -5 to 30. Then we also want to have our y-intercept as well. So we want to go down to we said -56. So -56 to +56. We can see a good picture of everything that's kind of happening in the graph, and then from there you may need to just zoom out a little bit farther, and we can see our minimum is very far down, but most of our features are kind of centrally located right here. So using the x-intercepts and the y-intercepts is a good way to at least have a starting point for your graph window. For what's the equation here, this is very important and something that will be asked about on a final exam for sure. So some of these examples are easy. So we're basically, for each of them, going to take our x-intercept and turn that into a 0, and then turn our 0 into a factor, and then that will kind of build out our whole equation. And we're going to be looking at just the factored form here. So our x-intercept is 4, 0. So that is when x is equal to 4. And then we would kind of make that subtracting 4 from each side. So now we have x minus 4 is equal to 0. So we know x equals 4 is 0. We have our in-between step. And then we would just kind of make it into x minus 4 as a factor. And this one only has one factor. So we have a repeated 4, 0 right here. And so then we would have x minus 4 as one of our factors already. So then we would have to deal with our second one of 0, 0. So if I know that x is equal to 0, well, I'm basically just doing x minus 0 equals 0. So sort of our factor is kind of x minus 0. Let's draw that again. We have x minus 0. But what you can really do, instead of writing out x minus 0, you probably would just end up kind of getting rid of the 0 part and just writing it like this. But also keep in mind that we can kind of just leave as just an x value for 1. So we kind of have just x minus 4 times x. And then you can also put the x at the front if you wanted to. So we could say that the whole function for number 2 would end up being x times x minus 4. So now I want you to try number 3 and 4 on your own, and then we'll do number 5 together. So go ahead and give that a try. We are now looking at our answers for numbers 3 and 4. So for number 3, just remember that like x equals -2 means that x plus 2 would equal 0, like we did up at the top in number 1. And then our factor would be x plus 2. And they end up being a lot of the times the opposite number, since they're kind of undoing operations. And then you can see in our orange part here, we have x minus 0 in the middle. Normally, you will have the x at the front, so I just moved the x from the middle to the front. And then my answer was x times x minus 2 times x minus 4. And then number 4, we have the same sort of thing. So that answer was x times x plus 4 times x minus 2. For number 5, I want to take a little bit more time on it. The -5, 0 is just like before. It would just end up being x minus 5, x plus 5. And then the 3, 0 part would end up just being x minus 3, just like we saw in the other problems. But now the last one, the 1/2, 0, ends up being a little bit different. So if we had that as an answer, that means that x equals 1/2 is going to be a 0 if that's our x-intercept. So if I kind of doubled both sides, I'd end up with 2x equal to 1. And then if I subtracted 1, because I got to make it equal to 0 again. So that would end up being 2x minus 1 equals 0. So that 2x minus 1 part is going to end up being our last factor here. So sometimes you'll, like you saw in earlier parts of these 3-part lesson, that you might have factors that aren't just linear with just x. Sometimes you'll have a coefficient in front of x. And that makes it a little bit tougher. And this is something you could check using Desmos to see that you've taken the x-intercepts and turned them into polynomials that would match it. And you can check that pretty easily using Desmos. Our lesson synthesis here is kind of just some general things. I want you to kind of think about what you've learned so far during these 3 parts of the factors and zeros lesson, and what you think the relationship is between features of graphs and equations of functions, and how zeros and factors play in with that. And also think about what questions you might have about that relationship between factors, zeros, and graphs, because they will become more important as we get further along into graphing polynomials. So lastly, we're going to take a second to try this final cool down problem, which the stuff we worked on 2 slides ago. So take a moment now to try this problem out. We're now looking at the answer. One example of a polynomial that would have intercepts on the x-axis at -7, 8, and 15 would be the polynomial you see at the bottom. And you can see my steps for each of them color-coded. If you're, for instance, you're starting out at x equals 8 as your x-intercept, x minus 8 equals 0 is your 0 part, and your factor is x minus 8. And then you can see that kind of coming down to being the factor down here. And do the same thing for green and purple parts above. Keep in mind that this is only one polynomial that would fit this. You can put in basically any a value at the front here, no matter what that a value is. You would be able to have your x-intercept stay the same, just like we saw in earlier parts of this total lesson. And that shows that there's lots of different possibilities, but we're looking for just any polynomial that goes through those particular x-intercepts. And that concludes our 3-part lesson in total on factors and zeros of polynomials. Thank you for watching.